You open your AI chatbot, you type in your prompt, and you hit enter. What happens next? We're pulling back the veil on the hidden backbone behind every AI response you see. Beneath the Oklahoma sky sits an unassuming concrete building, an AI factory built for one purpose: speed. I'm standing in front of Cerebras' brand new data center, which they just did the ribbon cutting for, and now they are serving 44 exaflops of new compute power to their customers. It is the fastest AI infrastructure on Earth, and today we're gonna get a tour and we're gonna be able to speak to the CEO. This facility delivers 44 exaflops of new compute to customers, the fastest AI infrastructure on Earth. Today, we're going inside to see how Cerebras pushed past the traditional chip limits and built this behemoth from the ground up, starting with why they chose Oklahoma.
Andrew, thanks for having us. We are here at your new Oklahoma data center for Cerebras. Why did you choose Oklahoma?
There are a lot of reasons why you pick a location. You're looking for a place with reasonable labor costs. You're looking for a place you can build, you can expand. You're looking for a place with reasonably cost power. And we found all of those here in Oklahoma City.
Preparing for Oklahoma's weather shaped the building itself, reinforced concrete designed with tornado resilience in mind.
When you're choosing a location, do you have to also think about the energy mix? Do you have to think about how you're going to secure the data center? I mean, Oklahoma is known for tornadoes. How do you think about that?
Sure. I think generally you think about the construction of the building and what it's rated for. That hits you in your cost of insurance. Your insurer will come out and look at the building and be sure it's rated for whatever natural disaster is in the area. So if you have a data center in Santa Clara, California, which we do, or Stockton, California, those are obviously rated and prepared for earthquakes. This is a facility built of concrete and is prepared for tornadoes.
Speed here comes from one radical idea: the Wafer scale engine, the largest processor ever built.
How big is a traditional chip as compared to what we're looking at here?
So this is a chip that's 46,250 square millimeters. So it's the size of a dinner plate for those of you who don't do metric. A traditional chip was large if it was over 750 square millimeters. So this is the size of a dinner plate, and the largest other chip is the size of a postage stamp, or approximately the size of your thumbnail.
Each one of these systems has one chip, and it sits behind the power supplies, and it sits upright. Traditionally, people put chips on motherboards like this.
Right.
We put it upright, and it sits about halfway back.
Got it.
Okay? On the other side of it, it's cool.
The breakthrough wasn't just size, it was keeping memory on the chip, eliminating the off-chip latency that slows traditional GPUs during inference.
We have all our memory on the chip.
Okay.
Other people have their memory off chip. All right?
So that latency time between...
That latency time is the reason GPUs are slow at inference. That's it.
Got it.
Just that. And we're 2,500 times faster at getting to data and then using it.
Okay.
That's what gives this massive performance advantage. Memory bandwidth.
One wafer draws 18 kilowatts. To move that heat, Cerebras adopted liquid cooling, an approach they began in 2017.
These are water-cooled machines, so they're unbelievably energy efficient. All right? The blue line is cold water coming in, and the red line is warm water going out. And what you see underneath is the way modern data centers are built with raised floors, so all the water infrastructure is underneath. And so you can see the cold water, the chilled water return. So you've got it chilled water. You've got the orange, which are valves. by a company called Belimos. And what they do is they tell us all about the water pressure and all the details so we can keep track.
All of it ties into a 6,000-ton chiller plant that manages temperatures and humidity deltas to keep the wafers in their sweet spot.
Okay, so we're here with Billy, COO of Scale Data Centers, and tell us exactly what we're looking at behind us and how the water is cooled in these machines.
Yeah, so it's a 6,000-ton liquid-cooled chiller plant producing chilled water to Cerebras' servers. We got room to grow another 6,000 tons of chiller capacity. So as Cerebras grows, we can grow chillers. We send it off at 42-degree water. They take it, we hit it on heat exchangers and heat it back up to about 70 degrees is what we're sending to the wafer chip itself. It returns back. We got cooling towers on the outside that takes that heat exchange, evaporates it to cooling towers outside the air, and then it's just a big cycle, keeps going.
Why do you heat it up before sending it to the wafers?
Well, we heat it up because it will make their wafer more efficient. It can't handle that cold of water because at dew point, you get moisture in the servers and you get condensation in the servers. So you got to keep that delta T, about a 15-degree delta T, to keep moisture out of the servers.
And what technique is actually cooling the water in these machines?
The chillers, the condensing water. So there's cooling condensing water that actually cools it off. The chiller actually produces the cooling itself.
Okay.
What you can tell here is the temperature of the inlet water, and you can tell the temperature of the outlet water, right? That's exactly what's going on, and we're able to capture this for every CD, every part.
High-speed compute demands steady power. The primary source here, natural gas converted into electricity, with batteries bridging about 5 minutes until 3-megawatt generators spin up. How they maintain nearly uninterrupted service.
This is a 3-megawatt generator. It runs on diesel or liquid natural gas. And it is one of the generators that powers the room you just saw.
Okay, so this is a backup generator, or this is currently being used to power it?
This is a backup generator.
Yeah.
This is a generator that is used if the primary sources come down.
And what is the primary source?
Primary source is natural gas that has been converted into electricity, and then delivered to the room.
Unbelievable. And I think one of your colleagues told me this is one of 4 in the entire state of Oklahoma.
Yeah, this is a big boy. These are unbelievably cool generators. This is how we're able to attain nearly perfect uptime, right? Is that if there's a power outage for any reason, these bad boys kick on. All right.
Instantly, no downtime between the switch.
Between the two, you have a battery backup.
Right.
So the way backups work in data center is you have batteries whose job it is to get you about 5 minutes. So if something comes down, the batteries kick on
That's all
immediately.
you need before this kicks on.
This kicks on. It takes about 5 minutes before, usually 3, but you provision 5. And then this bad boy is delivering all the power you need and you stay up. Right? And there's 3 of these.
So let's say the power goes out. Do all 3 of these machines kick on at the same time, or are these failovers?
Each one of these is 3 megawatts. All right. So we have power coming in different feeds depending on how much power we need. Right. 1, 2, or 3 of them will kick on for the room you just saw.
Right. So when I'm hearing from other AI factory builders, they're talking about gigawatt scale, but they're talking about energy consumption rather than inference output.
Correct.
But obviously you guys are the fastest supercomputer in the world. Why are there different metrics? Why are they talking about it differently?
Gigawatt is a way to describe the capacity of this entire building.
Okay.
All right. It is a way to say how much power can we deliver to the compute total. And nobody has a gigawatt today.
Right.
These are still in the future dreams. This is a, top 50 facility in the world, is what you're seeing right now. There are bigger, but there are a few that are more efficient.
I'm wondering, because the energy is the input, the compute is the output. Why not talk you guys talk about the output. Why doesn't everybody else talk about the output? Is that because you guys are just so much more efficient?
Yeah, because our numbers look better than theirs if you talked about output.
Got it. Yeah, simple as that.
So far, we have seen OKC1, which is the first data hall. That one's up and running in production. What we're going to see right now is OKC2, the second data hall that will be in production in 3 or 4 weeks.
Amazing.
All right, let's go.
Campus is expanding fast. OKC2, the second data hall, is nearing completion, adding capacity for the next wave of high-speed workloads.
Oh, it's like pretty significantly built out already.
Right. So, in the process of building, you deploy the racks and the cabling. So that's step one, right? You roll the racks in, and all of them should be set up exactly the same way. So those were racks. That's step one, okay? Step two is the machines get inserted.
When these get turned on, how much additional compute capacity is that going to offer?
This room will add about 20 exaflops. So about 10 times the largest computer that the US owns in the Department of Energy.
The systems are manufactured and assembled in Milpitas, California, keeping the hardware pipeline domestic.
You are choosing to build in the United States, as well as you mentioned, the actual modular Cerebras units are built in the United States. Why did you make that decision? What does that give you?
We manufacture in Milpitas, California. We are committed to manufacturing in the U.S. We package, we assemble. The final systems you saw are manufactured in the U.S. We think that that's an important part of being a good citizen in this economy.
A decade ago, the entire system, hardware and software, was still just an idea. The team pushed through a period when it looked impossible.
There was a 15 or 18-month period where we couldn't do it. We were spending $8 million a month, and we hadn't solved the problem.
Wow.
And then, yeah, that's a lot of money. And our board stayed with us. We used good engineering methodology. Each failure, we root caused. We figured out what we had to do not to make that mistake again. Bang, we made another mistake. We bumped into something else again and again and again. And then one day, we set it up, and it worked. And we're standing in a lab about the size of a small office in a building that wasn't designed for hardware. We had the windows open. We drilled a hole in the wall for hot air to be piped out. And the 5 founders, we stood there for 30 minutes and we couldn't speak. That we had solved a problem that the best in the world over 75 years were unable to solve.
Expect the fastest real-world transformation in medicine and education, 2 fields overdue for change that benefit directly from faster, more accurate models.
What aspect of societal change from AI are you personally most excited about?
AI in medicine. I think AI has a tremendous amount to offer there, in part because our techniques previously have been sort of rudimentary. I think we should be able to knock years off the drug design process. Today, it's 17, 19 years to develop a drug from scratch. We ought to be able to get that to under 10. I'm also excited about education. I think in many ways, the way we teach children has been unchanged since Alexander the Great was tutored by Aristotle. AI offers a very different opportunity to change the way we teach children.
Well, Andrew, thank you so much. Congratulations on everything. And I can't wait to see this continue to be built out.
Well, thank you so much for having us.
Thank you, Andrew.